Hello, welcome to the course SJPHY1B01 Mechanics 1. The contents of this course is taken from An Introduction to Mechanics by Klepner and Kolenko. We will continue to discuss topics from Chapter 4, Work and Energy. In the last class, we have seen how to integrate the equation of motion in one dimension. And when you do that, you will arrive at a very important theorem in physics known as work-energy theorem. So if you recollect our problem in one dimension, we had a particle which is originally at a position A, denoted by coordinate XA, and it moves to another position B, denoted by coordinate XB, under the influence of a force F of X. Remember, force is always represented as a function of position, right? So if VA is the velocity at position XA and VB is the velocity at position XB, then you can write half mVB square minus half mVA square equal to integral XA to XB f of x dx. So basically we have taken the equation of motion in the one dimension and integrated it with respect to position. Now let's try to understand what is the physical meaning of this relation. Half mv square is nothing but kinetic energy K. So you can write half mva square is kinetic energy at position A, which you can call as Ka, and half mvb square is kinetic energy at position B, which you can call as Kb. So left hand side is Kb minus Ka. What is the meaning of the right hand side? So force into displacement is nothing but work done, right? So integral XA to XB f of x dx is work done by the force on the particle as it moves from initial position A to final position B, and you can call it as WBA. So when you do the integration of the equation of motion with respect to position, you get the relation work done WBA equal to change in kinetic energy Kb minus Ka. This is known as work energy theorem in one dimension. So the net work done by the forces on an object equals the change in its kinetic energy. So this theorem talks about the interrelation between work and energy, and if you notice, the unit for work and energy both are same. So in SI unit, the unit is joules, which is 1 kilogram meter square per second square. So how do you derive the unit? Basically, you take the simplest relation about the concerned parameter. So in this case, we are talking about work. Work is force into distance. And what is the simplest relation for force? Force is mass into acceleration, right? So unit of mass is kilogram, unit of acceleration is meter per second square. So you have kilogram meter per second square multiplied by distance whose unit is meter. Thus you get the unit kilogram meter square per second square. This is the SI unit. And in CGS unit, this is the old metric where the units are centimeter, gram and second. Whereas in SI you have meter, kilogram and second. So in CGS unit, the unit of work or energy is erg. One erg is defined as 1 gram centimeter square per second square, which is 10 to the power minus 7 joules. Now, what is the application of work energy theorem? In certain cases, you can analyze the motion of a classical mechanical system without solving the equation of motion using the work energy principle. You can derive some important physical insights using this simple theorem. Let's see one such example. Vertical motion in an inverse square field. So a mass m is shot vertically upward from the surface of Earth with initial speed v0. Assuming that the only force is gravity, find its maximum altitude. Also calculate the minimum value of v0 for the mass to escape from the surface of Earth completely. Sorry for mass to escape Earth completely. So basically escape the gravitational field of Earth. Okay. So if you throw an object upward from the surface of Earth, you know that as it moves upward, the gravity tries to pull it down. So the velocity decreases. Finally, when it reaches the maximum height, the velocity is 0. So you are asked to calculate that altitude. Also, you know that if you launch an object from the surface of Earth with velocity above a certain threshold value known as the escape velocity, then the object can break the gravitational field and go away from the Earth, right? So if the velocity is below escape velocity, then the object will fall down. If the velocity is above escape velocity, then it can escape the gravitational field of Earth completely. Okay, so we are asked to find out these two parameters. Okay, we know that the gravitational force at a distance r from the center of Earth is given by minus gmem by r square, where me is the mass of Earth. Okay. Since you are launching the object from the surface of Earth, at the starting point, the value of r is the radius of Earth, re, and after some time t, it has reached a height r with respect to the center of Earth. So you are going to analyze this motion. Okay. So this is a one-dimensional motion. Even though it is not strictly along a single direction, if you look at the direction as a whole, it is consistent. In that way, you can say this is a one-dimensional motion. Okay. So you can apply the work energy theorem onto this motion. So the kinetic energy at the final position, which is k of r, minus kinetic energy at the initial position, which is k of re, equal to integral re to r f of r dr. You know the expression for f of r, substitute that, so you get on the right hand side minus gmem integral dr by r square. Integral of r square is minus 1 by r, so you apply the limits. Then kinetic energy at position r is half mv of r whole square. And kinetic energy at position re, we know that the initial velocity is v0, so at this position kinetic energy is half mv naught square. And on the right hand side, when you apply the limits, you get gmem into 1 by r minus 1 by re. Now we need to calculate what is the maximum altitude the object can reach. Okay. So we know that at the highest point the velocity is 0. So v of r equal to 0. When you put this information back into this equation, you can see the first term vanishes. So you have minus half mv naught square equal to gmem 1 by r. Since we are talking about the maximum r, I am going to put a subscript max here. So 1 by r max minus 1 by re. From this I can write v naught square equal to 2 gme into 1 by re minus 1 by r max. It is a good idea to introduce non-familiar constants whenever possible. For example, we know that the acceleration due to gravity, small g, equal to gme by re square, right? So from our previous expression, instead of gme, I can write gre square. So in terms of acceleration due to gravity, I can rewrite my equation as v naught square equal to 2 gre square into 1 by re minus 1 by r max, or rearrange the terms, you get 2 gre into 1 minus re divided by r max. Now from this you can get the expression for r max as r max equal to re divided by 1 minus v naught square divided by 2 gre. So the first part of our problem is what we have found out what is the maximum altitude. Next we need to find out what is the escape velocity. So as I said, if the velocity is below the escape velocity, then the object will fall back onto the surface of Earth. On the other hand, If the velocity is greater than or equal to the escape velocity, then it can break the gravitational field and move far away from the center of Earth. In other words, you can extend R max all the way to infinity if your velocity is greater than escape velocity. So from this expression, I can calculate what is the escape velocity. So basically, I push R max all the way to infinity. So I can rewrite this equation as V escape square equal to 2GRE square into 1 by RE minus, what is the R max now? It is infinity. So this is minus 1 by infinity. 1 by infinity is 0. So V escape square equal to 2GRE. From that I get the expression for V escape as square root of 2GRE. You can quickly plug in the values and find out what is the magnitude of escape velocity. So this is square root of 2 into 9.8 meter per second square multiplied by radius of Earth, which is 6.4 into 10 to the power 6 meters. So you get the value of escape velocity as 1.1 into 10 to the power 4 meter per second or 11 kilometer per second. So if you launch an object with velocity greater than or equal to 11 km per second, it can move far away from the surface of Earth. If the velocity is less than this particular value, then the object will fall back to the surface of Earth. So this is how you get important insights about a physical motion without solving the equation of motion by applying the work energy theorem. Same way, you can also calculate what is the energy needed for launching an object. For example, you have a spacecraft of mass 50 kg. So initially the spacecraft is at rest at the surface of Earth. So the kinetic energy, initial kinetic energy is 0. And when you are launching the spacecraft, obviously you are launching it with escape velocity. So the final kinetic energy is going to be half mv escape square. So since the initial kinetic energy is 0, the changing kinetic energy is nothing but the final kinetic energy, right? So work done equal to half mv escape square. You plug in the values, you get the result 3 into 10 to the power 9 joules. So far we have been dealing with equation of motion in one dimension, that is a specific case. Now let's take the general case, that is integrating the equation of motion in several dimensions. So as always, start with our fundamental equation F is equal to ma or F equal to m into dv by dt. The left hand side is a space dependent term and the right hand side is a time dependent term. In the case of one-dimensional motion, we integrated the equation with respect to position, and to generalize this, consider what happens when the particle moves a short distance delta r. So originally it was at this position, and after some time t, it has moved a distance delta r under the influence of the force F. Okay. Now if we assume that delta r is very small, for all practical purpose, the force F can be treated as a constant over this displacement because the displacement is very, very small. Now what you do is take the dot product of this equation with respect to delta r. So on the left hand side and right hand side, you take dot product with delta r. So your equation now becomes F dot delta r equal to m dv by dt dot delta r. So I hope you know the meaning of dot product. So if you take dot product of two vectors A and B, this is magnitude of A multiplied by magnitude of B multiplied by cosine of angle between them. So in this case, F dot delta R is magnitude of F multiplied by magnitude of delta R multiplied by cos theta. And V and delta R are not completely independent. For a sufficiently short length delta r, you can approximate the velocity to be a constant. Then you know the relation velocity v equal to delta r by delta t, or delta r equal to v delta t. So on the right hand side, instead of delta r, now I can write v delta t. So I have m dv by dt dot v delta t. I can simplify this even further. We know that dot product is commutative, which means a dot b is same as b dot a. So dv by dt dot v is same as v dot dv by dt. And v dot dv by dt I can write half d by dt v square. You can quickly cross check this. For any vector a, let me start from the final result, half d by dt a square. A square is nothing but a dot a, right? Dot product of a vector with itself is nothing but square of its magnitude. Okay, so half d by dt a dot a. Now this is a simple product rule. How do you find the derivative of a product? First term dot derivative of the second term plus derivative of first term dot the second term, right? So you have half into 2a dot dA by dt, 2 and half cancel, you have a dot dA by dt. So this equation is valid. Now let's put everything back into our original equation. So on the left hand side I have f dot delta r. Now on the right hand side, after doing all these simplifications, I have m by 2 d by dt v square delta t. So remember, originally we are at position A denoted by position vector Ra. Under the influence of the force F of R, we have moved to the final position B denoted by position vector Rb. Now what we are going to do is we will divide this trajectory into n small segments, each segment having a length delta r. So if you look at segment J, it has a length delta rj, and the position vector of this segment is rj, and let's assume that the velocity of the particle at this position is vj, and the time taken for the particle to cross the jth segment is delta tj. So basically we are adding a subscript of j here. Now for the jth segment I can rewrite this equation. So at the jth segment the force is F of rj dot delta rj equal to m by 2 d by dt vj square into delta tj. So this is for the jth segment. So I can write this equation for each of these segments and add all these together, then I'll get the total equation for the entire motion, right? So you add all this equation, you get summation over j f of rj dot delta rj equal to summation over j m by 2 d by dt vj square delta tj. Now what happens when you decrease the length of each of the segment? So imagine that your trajectory is of 10 centimeter. You have divided it into 5 segments. Each segment will have a length of 2 centimeter. Now if you decrease the length to 1 centimeter, what happens? The number of segment increases to 10, right? Originally you had 2 centimeter segment, 5 of them. Now you have 1 centimeter segment, 10 of them. So basically when you decrease the length of each segment, the number of segments increases. So let's take the limiting scenario. You decrease the length of each segment to 0. So you're approaching 0. What happens to the number of segments? It approaches infinity, right? And from calculus, you know that an infinite summation is nothing but an integration. So you can replace this summation with an integration now. So on the left hand side, you have integral f of r dot dr. On the right hand side, you have integral m over 2 dv by dt into dt. So, yeah, m by 2 d by dt v square dt. Sorry about that. Okay. And look at the limits of the integral. So originally you are at position A, which is denoted by position vector Ra. Let's assume that the corresponding time is Ta, and the final position is Rb, and the corresponding time is Tb. So on the left hand side you have integration from Ra to Rb. and on the right hand side you have integration from TA to TB. Now let's solve the right hand side. M by 2 is a constant that comes outside the integral. So you have integral TA to TB d by dt v square dt. So integral of the derivative, this is nothing but the term inside. So you have half mv square, apply the limits from TA to TB. And velocity at time TB is VB and velocity at time TA is VA. So the right hand side is half mVB square minus half mVA square. So when you put it back into original expression, you get integral RA to RB f dot dr equal to half mVB square minus half mVA square. So once again you have shown that the net work done by the forces on an object equals the change in its kinetic energy. So this is work energy theorem for multi-dimension or for several dimension. Now one thing you have to remember is that in the case of one-dimensional case, when I say v square, I mean explicitly vx square or vy square or vz square. Only one dimension is there. In the case of three-dimensional, I have three components x, y, z. So v square is vx square plus vy square plus vz square. All we have done is to integrate this equation of motion with respect to distance. But because we describe each step carefully, it looks like many operations are involved. This is really not the case. The whole argument can be stated in a few lines as follows. So if you look at the summary of what we have done over the last 3 slides, this is very simple. We have taken the equation of motion, we have integrated it with respect to position, and instead of dr we can write v dt. Then you write dv by dt dot v in terms of d by dt v square. Do this integration, apply the limits, then you get half mvb square minus half mva square. So this is the gist of what we have done. So in fact, if you look up a guidebook, this is the only information you are going to get. But noticeably, the mathematical rigor is lost, right? So when you have done the actual integration over the 3 slides, a lot of mathematical details are there, right? All those details are very important. Because many a time when you look at the final result, it is an outcome of a lot of approximation, a lot of limiting scenarios, etc. Okay. And all those mathematical details are important, because if you don't know the mathematical details, you may interpret the results wrongly, or you try to apply a theorem in wrong conditions. So all those things should not happen. So whenever you study a physical theorem, try to understand it in its full mathematical rigor, so that all the mistakes can be avoided. It is also important that in the midst of all these mathematical details, you don't forget the fundamental physical picture, because both are equally important. Physics speaks in the language of maths, but if you talk only in terms of maths, then the physics is lost. So both are equally important, and give due importance to both. So in the next class, what we do is we will derive the work energy theorem in the general case of several dimensions, and we also discuss some of the important applications of work energy theorem, especially in 3-dimensional motion. Thank you.